It's been called liquid sunshine and the foundation of empires, a title that fits considering gold fuels a $200 billion industry every year. But how is gold actually made? Hollywood shows treasure chests and dramatic heists, but the real story is a lot more complex and far less glamorous. We're digging deep, literally, into the secrets of mining, chemistry, and extreme heat that turn worthless ore into the ultimate symbol of wealth. Along the way, we'll reveal the alchemist's secret that makes this transformation possible, a process involving chemicals that most people would never expect to find in a gold mine. But before any of that can happen, there's one big question. How do you even find gold buried somewhere in the vastness beneath our feet? Don't forget to like the video. The hunt for hidden gold starts long before any shovels hit the ground. Geologists and exploration teams use a mix of science, technology, and a bit of luck to zero in on areas that might hold gold. It all begins with detailed geological maps which highlight places where the right mix of pressure, heat, and minerals could have created gold veins millions of years ago. These maps act as the first filter, helping experts focus on regions with the right geological story. Next comes soil sampling. Teams collect dirt and rock from targeted spots and test them for tiny traces of gold, sometimes just a few particles in a whole bag of soil. This step is all about precision, using sensitive equipment to catch even the faintest signal that gold might be nearby. It's a slow, methodical process that can take months, but it's crucial for narrowing down the search. But the hunt doesn't stop there. Companies invest heavily in remote sensing and geophysical tools like magnetometers and seismic surveys to narrow down targets even further. Remote sensing uses satellites to scan the Earth's surface for subtle clues, maybe a slight color change in the soil or a pattern that hints at hidden quartz veins. Geophysical surveys dig deeper, measuring magnetic fields or sending seismic waves underground to map out what lies beneath. These methods let geologists see below the surface, helping them spot promising rock formations or structures that could host gold deposits. On the ground, geologists study rock outcrops and formations, looking for host rocks that are likely to contain gold. Quartz is a favorite. Those white or translucent veins running through the earth often serve as natural highways for gold to flow and settle. Sometimes the clues are found in old riverbeds or alluvial deposits where water once carried gold downstream and left it behind in the sediment. Each piece of evidence adds to the puzzle, guiding the search team closer to a potential jackpot. The suspense builds as teams move from map analysis to fieldwork, gathering samples and poring over data. Every positive reading raises hopes, but the risk remains high. Months or even years can pass before a promising site is confirmed. When it finally happens and the data points to a real deposit, the mood shifts. The quiet work of surveys and sampling gives way to the next phase, where the focus turns from searching to extracting. After pinpointing a site, it's time to swap high-tech scans for raw muscle and machines. Welcome to underground mining. This is where the real challenge begins and where the story of gold takes a turn into the unexpected. Extracting gold from the earth isn't just about muscle and machinery, it's about precision and chemistry. Once a promising deposit is found, miners head deep underground, sometimes more than 500 meters down, to reach the gold-bearing rock. It's a tough job. The tunnels are hot, cramped, and filled with the constant noise of drills and blasting. The gold itself is hidden, locked away in tiny grains spread through the rock, barely visible even under bright lights. Getting at it means breaking up the rock with explosives and hauling tons of ore to the surface, all while working in an environment that demands both strength and accuracy. At the surface, the real transformation begins. The ore goes through a series of crushers that smash it down to rough gravel, then even finer grinders reduce it to the texture of sand. This isn't just about making the rock easier to handle. Pulverizing the ore exposes every possible gold particle, setting the stage for the next step, the chemical extraction. Enter cyanide. the alchemist's secret at the heart of modern gold mining. It's a chemical with a dangerous reputation, but in this controlled process, it's essential. The pulverized ore is mixed with water and cyanide in large tanks, forming a thick slurry. Here's where chemistry takes over. The cyanide dissolves the microscopic gold, pulling it out of the rock and into the liquid. Air is pumped in, adding oxygen that triggers the reaction, allowing the cyanide to bind with the gold and form a gold-cyanide complex that's soluble in water. And while cyanide is the alchemist's secret, it's stored and neutralized in lined tailings ponds to protect nearby ecosystems. Picture those massive tanks churning as air bubbles through the slurry. It's not glamorous, but it's critical. The gold is now separated from the rock, but it's still mixed with a lot of leftover material. That's where filtration comes in. Huge rotating drum filters spin away the slurry's solids, leaving behind a liquid brimming with dissolved gold. The solids, now waste, are moved to secure tailings ponds, while every drop of the gold-rich solution is preserved for the next step. This murky slurry might not look like much, but it holds real value. What started as hard rock has become a liquid loaded with gold molecules. The process is all about squeezing out every last bit of gold, even when it's present in tiny amounts. And thanks to careful chemical management, the operation extracts gold efficiently while minimizing environmental risks. With the gold now dissolved and separated, the stage is set for a transformation that relies on heat instead of chemistry. The next phase will push the process to its limits, as intense temperatures turn that gold-rich solution into something you can actually hold. Here's where things get intense. The gold concentrate is ready for a serious upgrade in the smelting stage. Operators start by mixing the concentrate with flux, a blend of silica, borax, and oxidizers like manganese dioxide and sodium nitrate. This cocktail isn't just for show. Each ingredient helps loosen impurities by lowering their melting points, making it easier to separate them from the gold. Once everything's mixed, the batch goes into a furnace built to handle the heat, over 1600 degrees Celsius or 2912 degrees Fahrenheit. The furnace slowly turns so every speck of concentrate meets the full force of 1600 degrees Celsius heat. Missed spots mean lost gold. Inside, the gold and impurities melt, and something critical happens. Everything separates by density. Gold, being much heavier, sinks to the bottom. The lighter impurities float up, forming a layer called slag. Operators carefully skim off the slag, but they don't just toss it out. Samples get checked to make sure no gold is hiding in there. If they find even a trace, the slag goes right back in for another round. It's all about making sure not a single gram of gold is lost in the process. The melting isn't just about brute force, it's about control. The furnace's rotation means the heat reaches every bit of the mixture, so impurities can't cling to the gold. Timing and precision are everything. If the process goes too fast or too slow, some impurities might stick around. And that's not an option when you're dealing with something this valuable. When the gold has settled at the bottom and the slag is gone, it's time to collect the molten metal. Operators tilt the furnace or use special channels to pour the liquid gold into molds. Watching it flow is something else, a stream of glowing metal that fills the molds and cools into solid bars. These are called doré bars. They look impressive, but they're not quite there yet. At this point, doré bars are about 80% gold, with the rest made up of silver, copper, and other trace elements. To reach the level of purity needed for gold bullion, 99.9%, the doré bars go through one final step. This is where science steps back in. Refineries use processes like electrolysis or chemical precipitation to remove the last bits of impurity. Electrolysis, for example, uses electricity to pull pure gold out of a solution, leaving everything else behind. Chemical precipitation can also be used to separate gold from remaining metals. It's the final act in the journey, turning those rough doré bars into the bright, pure gold bars you see in vaults and jewelry stores. So, from the chaos of molten metal and the careful removal of slag, what started as a hidden speck in rock becomes a bar of nearly pure gold. This moment marks the end of an extraordinary transformation, one that's powered by chemistry, heat, and a lot of patience. But the story isn't just about the process. There's something bigger behind gold's journey. A story about human ingenuity, chemistry, and why this metal has held its value for thousands of years. Gold's journey from raw ore to refined bullion is a showcase of innovation and chemistry. Each stage, from the hunt underground to the final pour, relies on careful planning and technical skill. And as we've seen, every drop of cyanide and slag is managed under strict regulations to balance our quest for wealth with care for the planet. Even as digital coins rise, nothing matches the tangible shine and historic stability of a true gold bar. If this peek behind the scenes of gold's alchemical journey sparked your curiosity, hit like and subscribe for more deep dives into the science behind everyday wonders.